So I am Aurel Page, and I am lecturing on computational mathematics with a focus on number theory. And today's lecture is going to be about linear algebra and lattices. So as a start, I want to give you a quick reminders of the first two lectures. First lecture, we talked about complexity. So reminder, the complexity is the running time as a function of the size of input for a given algorithm. And I gave you four broad complexity classes just to give a rough idea. Fast algorithms, quasi-linear in the size of the input. Medium, polynomial but not quasi-linear. Slow, sub-exponential but not exponential. And very slow exponential algorithms. We discussed complexity for various arithmetic operations, basic operations on integers and polynomials fast, basic operations on matrices, and factorization of polynomials that can be done in polynomial time, and factorization of integers. This is harder. We only have slow algorithms for that. In the second lecture, we first discussed a little bit reconstruction algorithms, which allow you to recover an object from specializations or approximations. And we have fast algorithms for reconstruction. So they can be of various types, modular or multimodular or real approximations of integers, evaluation, interpolation of polynomials, continued fractions to recover rationals from real numbers, and Padé approximants to recover rational fractions from power series expansions. Then we discussed algorithms for algebraic number theory. So a reminder of the basic algorithms that we went through. Computing the ring of integers, there's first a hard factorization step of a discriminant. And then prime by prime, we can compute a P maximal order with round 2 or round 4. This takes polynomial time. We can factor ideals. Again, there's a hard factorization step that of the norm of the ideal, but then it's only prime decompositions and valuations, and this can be done in polynomial time. We discussed computations of Galois groups, and really there are two different problems depending on whether you're given the Galois field as input or a subfield which has a potentially large Galois closure. And this gives different running times. And computing the class group and units of number fields, again, we have two settings depending on whether we assume the GRH, the generalized Riemann hypothesis for our algorithms, in which case we have slow but not exponential, I mean sub-exponential but not exponential algorithms. And unconditionally, we have only exponential algorithms. Okay, so today we are going to talk about two related classes of algorithms, linear algebra and lattices. Okay, so first linear algebra. So let's define a little bit what I mean by linear algebra problems. So we are going to work over a ring. And for a little bit, I want to think about this ring not even being necessarily commutative. And so what we call an R module is an abelian group with a linear action of R, like the action of R distributes over addition. Okay? And so if you can just think of a vector space, except that the field is not a field, it's a ring instead. So I want to distinguish two broad classes of problems because the second ones, we sometimes think about them as being linear algebra, but really they are harder than actual linear algebra problems. So what I call linear algebra problems is, for instance, you're given a matrix representing an R linear map, and you want to be able to compute its image, kernel, pre-images of elements, so that means solving a linear system, computing the determinant if it's a square matrix. These are linear algebra operations. And if you want to think not in terms of maps, but in terms of modules, so you can think of submodules of R to the n. So again, if you think in terms of vector spaces, that would be vector subspaces of k to the n, and you want to be able to do a few basic operations like sum, intersection, equality of submodules. So here I'm insisting just a little bit on equality of submodules of R to the n and not isomorphism. So why not? So I'm classifying isomorphism of finitely generated R modules in the second class of harder problems. I will show you an example just after this to show you why I really think of this as being harder. And so what I call representation theory problems is isomorphism of modules and things like basis, canonical form, invariance of R modules. So for vector spaces, these things are not actually harder than this. For instance, vector spaces a finite dimension, they just have a dimension. This is the only invariant, and you can compute it with the same techniques as you do that, and that gives you bases and isomorphisms, but in general, it can be harder. Okay, so let me give you an example of these two types of problems. So let's take R, which is Z joint a pth root of unity for some prime p. Okay, so if you want to test equality of submodules of R to the M, because this is just a finite rank over Z, equality of things in there, you can just see this as a Z module of higher rank, of rank M times P minus 1. So equality of submodules, it doesn't make a difference that you were thinking of R in the first place. You could have just thought of Z. And so you can reduce equality of submodules to just linear algebra over Z. It's not hard, even when P is large. On the other hand, the problem of isomorphisms of R modules for this ring, this is much harder. If you consider just the simplest case, which is taking two ideals inside of this ring, and instead of thinking of them as ideals, you think of them as modules, like they have an R action, then they are isomorphic if and only if this quotient ideal is a principal ideal. So it's actually a special case of the principal ideal problem that we discussed a little bit in the last lecture in the context of class groups. And this is much harder. Like for large P, we have no idea how to do this. Okay, and so just to give you an idea why I'm calling this representation theory, so for this particular ring, for instance, an R module that's essentially the same as an abelian group on which the cyclic group of order P acts, and it will act through this pth root of unity. Okay, so representation theory, classically, it has to do with group actions, linear actions of groups, and so you can generalize this as actions of other rings. Okay, so this is for the difference between these two types of problems. So we will actually mostly discuss the first type, linear algebra, because the representation theory problems are usually harder. So most of these problems are solved by using normal forms of matrices. So I will discuss a variety of normal forms. Yes, okay, so in the algorithms. So the first kind of normal form that we have are what I call one-sided normal form, meaning you have your input matrix and you're allowed to multiply it on one side by invertible matrices, so by invertible operations, and you want to make that some kind of normal form. So the basic property that you use for this kind of normal forms is the echelon property. Maybe I should draw a matrix. I mean, surely you've seen echelon forms. Okay, just one thing. All my matrices are made of columns. They act on the left on column vectors. And so, yeah. So an echelon form will be like this for me. So in each column, so look at each column, there will be a last non-zero entry. That's what I call the pivot. And everything to the left here must be 0. And maybe some part will be diagonal. So here you have coefficients. Zeros here. Maybe you have a jump. And then zeros here, etc. Okay, so this is usually the basic property that we use to define normal forms over various rings. And then depending on the ring, you want to add some conditions. So over many rings, these kind of normal forms can be used to have a normal form for submodules of R to the M, like a generating matrix that only depends on the module that you had. So you can compare submodules just by comparing the matrices in normal form. So a few examples over a field, you can use the reduced echelon form, meaning you're just asking all the coefficients to the right of a pivot to be 0. So here you would have to have zeros here. That's the reduced echelon form that you can define over a field. Over a principal ideal domain, you can use the Hermit normal form. This is very similar. You ask that the matrix is in echelon form, and in addition, the coefficients to the right of a pivot, well, you cannot necessarily reduce them to 0, but they should be reduced modulo the pivot. So like, okay, let me put an example with actual numbers maybe. If it's over the integers and you have it 10 here is your pivot, and then you can have anything here that is between, say, 0 and 10. Well, 0 and 9, sorry. 8, 1, 2, whatever. And that's another normal form. And so that's for PIDs. And when you start to adding 0 divisors to your ring, for instance, over Z mod NZ, where Z is not necessarily prime, then you need to add extra conditions. I'm showing you here an example for R, which is Z mod 4Z. So this has some 0 divisors. And if you look at these two matrices, they are both in echelon form. Okay, here you have one pivot and 1 0 column. Here you have 2 pivots, and to the left you really have zeros. And it's also reduced in the sense that to the right of a pivot, everything is reduced. So like here you have just a 0, so there's no condition here. To the right of 2, 1 is representative of the class Sieve mod 2. But these two matrices generate the same module, because if you simply multiply this matrix by 2, this column by 2, you get 0 and 6. 6 is just 2, so it's the same as this column. And then, well, you can just subtract this from this and you get this one. So these two generate the same module. So you need an extra condition to actually produce a normal form. And that's called the Howell condition. I don't want to give you details about this, just make you aware that you have to be more careful than usual when your ring has 0 divisors. So in this particular case, this is in Howell form. This is the normal form. And so in particular, over this kind of rings, the normal form doesn't have necessarily as number of columns the minimal number of generators of the module. Okay? This is a module that can be generated by just one vector, but the normal form has 2 vectors. Yeah. Okay, maybe just to justify a bit the interest of this, like just by looking at the pivots here, you can get the cardinality of the module, so, which is not the case here. Okay, so this is an overview of one-sided normal forms. Now let's look at the second kind, what I call two-sided normal forms. So you have your matrix and you're allowed to multiply it on the left and on the right by invertible matrices. And you're trying to get a normal form for this kind of operations. So for instance, over a field, you can always reduce to a matrix that is diagonal with coefficients a certain number of 1s and then some 0s. And that will essentially show you the rank of the matrix. Over a PID, you have what is called the Smith normal form, which is also a diagonal form with each coefficient dividing the next one. And in particular, this reveals the isomorphism class of the quotient by the image of the matrix. Okay, so you've probably possibly seen this with the Smith normal form. You can get this form for any finitely generated abelian group, a bunch of elementary divisors and then a certain rank. And the way you should think about it when you look at this form, like one of the two matrices changes the generators of your abelian group, and the other one changes the relations to put it in this special form. Okay, so already this type of a normal form actually has to do with what I called representation theory problems, in the sense that it reveals the isomorphism class of a module. So this is a bit of a deeper operation. Okay, third kind of normal forms that you could be interested in, normal forms up to conjugacy. So now you're allowed to conjugate your matrix by an arbitrary invertible one. And already this is you really need a very special ring R to be able to have a normal form for things like this. It can be quite hard to even decide if two matrices are conjugate over arbitrary R. Even over Z, it's not so easy. So mostly we'll look at fields in this case. So for instance, over algebraically closed fields, there is the Jordan form for matrices. Okay, I'm not going to give details about this, but essentially it reveals the eigenvalues and their multiplicities. Over fields that are not necessarily algebraically closed, you have something that replaces it, for instance, the Frobenius form, or there's also a rational version of the Jordan form. But what I would like to emphasize here is that even though the way it's written, it looks like it's a problem over R, really this is actually a problem over Rx, a slightly larger ring where you add one polynomial variable. And why is this? When you are given a matrix, so a square matrix, you can make it act on R to the n, and that allows you to define an action of the ring Rx by defining the action of x to be multiplication by your matrix. Okay? So that produces a structure of an Rx module on R to the n. And now this conjugacy relation, if you rewrite it like this, un equals mu, this means that u commutes with the action of x when you consider Rn as a module over Rx given by the matrix M or given by the matrix N. So doing this kind of conjugacy is actually looking at Rx module isomorphisms. And that's why it's harder when your ring R gets complicated. And why can you do it over fields in particular? It's essentially because when R is a field, Rx is a PID. Whereas when R is more complicated, it's not. Okay? Right, so these are the normal forms we will use. I mean, we'll mostly talk about the first few, the simplest ones. So let me give you just an overview of how you compute an echelon form over a fairly general class of rings. We'll just consider a ring in which you can do extended GCDs. So you have greatest common divisors and the corresponding transformation elements. So let me maybe write it on the board. Okay, I'll do it on the other side. So if you write this relation, AB equals 0D times I think I wanted you to be on the left, actually. So let me put it on the left. So if you write what this full matrix is, we'll want maybe U, V, X, and Y. And so this is AU plus BV and AX plus BY. And so the relation that we have here is that AX plus BY is D, so this is really the extended GCD that you usually have. If we are in this general setting where you don't make extra assumptions on R, it's not automatic that if you have GCDs, then you have invertible matrices like this that complete this, this equality. And that's why I put that in the assumptions. And so how do you use this for an algorithm? Well, you consider your matrix, and then you look at each row from the bottom to the top, and you use the first non-zero coefficient as a pivot. And using elementary operations like this, you can replace a pair of coefficients like this by a 0 and something else. And this way you can put zeros everywhere to the left of your pivot. And then you go to the next row, you choose a new pivot, you put zeros on the row, etc. And this will produce the echelon condition, and then you do some cleanup depending on the extra conditions that you have, like reducing coefficients modulo the pivot, etc. So if you count how many operations you do like this, so there is a loop over the rows, so that will be a factor of m. Then for each row, you look at all the coefficients on that row, so number of columns, that will be a factor of n. And doing one of the elementary operations will involve combining two complete columns together. So the number of operations that you do is proportional to the size of the column. So you get this kind of complexity, essentially cubic for square matrices. Okay? So this is the basic echelon form algorithm, but it has this cubic complexity like we had for basic matrix multiplication, the one that just uses the formula. And we would like to have something faster by exploiting the fact that we can multiply matrices faster, as we saw on the first lecture. So I will not give you the full details on how you do all the operations. I will just do a simple case. Okay? So the broad idea is that you will do operations by block, and by block matrices, and by doing these operations by block, you will, instead of multiplying just coefficients, you'll multiply big matrices, so that will factor out a lot of operations at the same time, and therefore exploit fast multiplication. So let me do this simple example on the board. I will just show you how to invert matrices using faster multiplication, assuming that everything goes well in the algorithm, that we are not in a special case. So we'll consider a matrix of size power of 2. Again, to simplify, you can reduce to that case. And you think of these matrices as being a matrix with 4 blocks of half the size. And then you will do the usual operations that you would do on this, except that you have to be careful about non-commutativity and the fact that, well, matrices are not always invertible, things like this. So let's assume that here D is invertible, so we can actually use it as a simple pivot. Then we can replace the second column by the second column multiplied by the inverse on the right. So so for that we used one inverse and one multiplication. Then we can make this coefficient 0 with a subtraction. So let me see. So get a 0 here. Oops. Then you can invert this one. I will assume that it's also invertible, etc. So you do this series of operations, and to get the actual inverse, you repeat the operations on the identity matrix, and that will give you the inverse of the original matrix. Okay, so now how do you analyze this algorithm? Well, you have to count how many of each type of operations you did. And if you count, okay, again, assuming we're in this special case where the two matrices that appear are invertible, we use 2 inverses of block matrices and a bunch of multiplications and additions. It doesn't really matter how many. Just a constant number. And so the total number of operations will solve a recurrence as usual for this type of algorithms. So it satisfies the following. So number of operations to do inverse is the cost of 2 inverses in half the size, plus a constant number of matrix multiplications, which we are assuming we can do in n to the omega for some omega. And if you solve this recurrence, well, what is important is that this is 2, and 2 is smaller than, well, I guess 2 to the omega is the important value. And then if you solve this recurrence, you realize that the solution is also big O of n to the omega. So we've grouped sufficiently many operations together in matrix multiplications to achieve the same complexity. You can even actually count more precisely, asymptotically, to how many block multiplications it's equivalent, and I think it's something like, it's maybe as fast as 3 multiplications or something like this. Okay, so I just, without actual details, I want to give you a few complexities depending on the ring. What we just saw was over an abstract ring in which we just counted the number of ring operations, but for actual rings, I mean, the coefficients can be bigger or larger, and you have to take this into account. So if you have a finite field, you have no problem because there's no coefficient explosion. So you just get the complexity that you expect times how much it costs to multiply elements in the field. Same over Z mod NZ. It's actually not a problem that it's not a field. So you just take into account the size of coefficients. When you start getting to infinite rings, well, consider, for instance, the Hermit normal form over Z, then you have to take into account coefficient growth. And you can see here that the complexity, it depends on the size of the input coefficients, but you also actually get one more in terms of the dimension because the size of the output can be much larger than the size of the input. Okay, so that's what comes with infinite rings where you can have coefficient explosion. So let me just give you, in a special case, a method to overcome coefficient explosion and actually achieve reasonable complexity. Oh yeah, what I should say, this HNF algorithm is not the obvious one where you just do elimination as we explained over an abstract ring. If you do that, it would be exponential because you could have an explosion of the size of the intermediate coefficients before you get to the end. So to get this complexity, you have to do something special actually. And it will be something of the same kind that I will describe now, but more complicated. So I will describe how to do the determinant over Z. Okay? And so the idea is simple. You actually use a reconstruction algorithm. You compute the determinant. So first you compute a bound on the determinant that you are going to compute. For this, you can, for instance, use the Hadamard bound, which tells you that the determinant is at most the product of the norms of the columns. That gives a bound. And then you compute the determinants modulo several primes, PIs, enough so that the product of the PIs is larger than twice your bound. And then from these determinants modulo the PIs, you do an effective Chinese remainder theorem to reconstruct determinant M modulo that integer and therefore the actual determinant. Okay? And that completely avoids a coefficient explosion. Okay, I didn't give the actual complexity, but this gives you a good complexity. I think that's a good time to make a break. So now I will describe some applications of linear algebra, especially in the context of number theoretic algorithms. So let me give you three broad class of methods that allow to reduce a problem into linear algebra. So I will say a few things about logarithms, Newton's method, and index calculus. Okay, so logarithms, quite obviously, can be used to turn multiplicative problems into additive ones and therefore linear algebra. So let's take a simple, an example from algebraic number theory, solving norm equations. You're given an extension between two number fields, f and k, and you're given an element in the small field, and you're supposed to solve the equation norm f over q of x equals a. So this is clearly a multiplicative problem, and so we want to use some kind of logarithms to solve it, to reduce it to linear algebra. So you can do it as follows. First, you consider the ideal generated by A, and you factor it. So that will give you a bunch of primes, and the point is that the set of primes that you'll obtain will have the property that A is an S unit. And then you can compute the groups of S units of F and of K, and now this is just a linear equation for a map from the S unit group of K to the S unit group of F. And so to make it actually linear, like in a way that you can solve it using matrices, you write A here as a product of S units, of the generators that you computed for your S units. And then you look for X as an S unit in K, in the top field. So you will look for the coefficients of the expression of X in terms of the generators of the S unit of K. And that will give you a linear system that you can solve using simply using linear algebra. And that gives you a way of finding the solution X if it exists. Sometimes it doesn't exist. Okay, so this is one possible use of logarithms. Let's look at a more complicated one. So if you remember in last lecture, I defined this general notion of saturation in an abelian group. And we applied it in an additive context where we were trying to compute the maximal order in a number field. Okay, so now we are going to think about it multiplicatively. So the problem is you are given a prime number and a finitely generated subgroup of the non-zero elements of F, and you want to compute the p saturation of H. So recall what this means. This means as long as you can take p powers of some elements of H, you take these p powers and you add them to the group until you can't anymore. Okay? So we had a naive algorithm to compute p saturation, which was to look at all the possible combinations of the generators with exponents between 0 and p minus 1 and try to see if they are p-th powers. So this is very slow because you're trying lots of different possibilities. So what we want is a way of detecting p-th powers to actually find them without trying many possibilities. And we will do that using logarithms and linear algebra. So what are necessary conditions for a certain product of the generators of H to be a p-th power? Well, first, all of its valuations have to be 0 mod p, if it's a p-th power. And also, if you reduce H modulo various primes Q, then you end up in a finite field and you have discrete logarithms, like expressing the elements as a power of the generator. And these discrete logs also have to be congruent to 0 mod p when you're a p-th power. So this gives you, in fact, an infinite set of conditions for an element to be a p-th power. And so you can combine them into the following algorithm, which is due to Post and Zassenhaus. So use a finite number of these among this infinite set of conditions to form a linear system modulo p that must be satisfied by the coefficients xi. You solve the system, so this is just a kernel mod p, and this identifies one or several candidates h that could be pth powers. Then you try to compute pth roots of these elements h, and this is just a polynomial factorization. You factor, you just find roots of x to the p minus h. So we can do that in polynomial time. If it fails, if you don't find a pth root, it means you didn't put enough conditions in your system, so you add more conditions. And well, it's actually possible to prove that these conditions, if you were able to put them all, they're actually sufficient for an element to be a pth root, a pth power. And then you repeat, because you should extract pth power until the group is saturated. Okay, so this is the p saturation algorithm, and so this was a multiplicative problem, and the important part here is where you used discrete logs to reduce it to a linear algebra problem. Okay? All right, second class of examples, Newton's method, or it's called Hensel's method, depending on the context. So you want to solve an equation f of x equals 0, where f is not linear, and you start from an approximate solution, and you want to make it better and better. And for that, you use the first order expansion of f. It will have a differential. It has to have a differential to apply the method. And you try to solve the linear system, differential at x naught of e equals minus f of x naught. And this is a linear equation in the term e. So this is the part where we reduce to linear algebra. And if you manage to solve this because of this first order expansion, you have found a new point which is much closer to being a solution than the previous one. So if you apply this, for instance, to finding the inverse of some A, maybe a matrix, or it's fairly generic, and you work out the method, this is the iteration that you get. So in fact, in this case, you don't even have any inverses anymore. You just have multiplications. So that was a first example. Another example that's actually useful for matrices is the Dunford decomposition. So what's this decomposition? You start with a square matrix M, and the theory tells you that it can be decomposed into some D plus N, where D is diagonalizable, and N is nilpotent, and the two matrices here are polynomials in M. Okay, so they commute with each other, they commute with M, they're actually polynomials in M. And so it's actually possible to do this using a Newton iteration. You take P to be the characteristic polynomial of M, so I didn't really talk about characteristic polynomial, but that's also a linear algebra operation that you can do. Then you take the square-free part of that polynomial, maybe it's going to have repeated factors, you want to remove them. And in particular, what you have is that f of m to the n is 0, always. And the d that you're looking for actually satisfies f of d equals 0. So m is an approximate, in this sense, root of f, and you're looking for an exact root, which is d. And if you simply apply the Newton iteration on this equation, starting from m, in very few, in fact, iterations, you end up with the matrix D, which is what you were looking for, with the property that the difference is nilpotent. I mean, you have to analyze this a bit to see that it works. Okay, third class of algorithms that I want to describe are index calculus algorithms, and here I'm going to give you an idea of how we perform 3 tasks for which I gave you time complexities but not the actual algorithms, namely factorization, discrete logarithms, and computation of class groups. Okay, so here is the general idea, and we'll see the examples just after that. Okay, so the idea is, broadly speaking, we have some kind of multiplicative problem, and we choose what we call a factor base. It's going to be a set of small primes over which we are going to try and factor elements. So typically, it will be the set of all primes up to a certain bound. And then, in some way, we generate random elements in our context, and we hope that they are smooth. So smooth means that they actually are a product of the primes that we selected as our factor base. So this will not always happen, but for your algorithm to work, you have to take a factor base that is large enough so that it actually happens somewhat often. And you call these elements, the ones that are actually smooth, you call them relations. They will give you, I mean, you'll see in the examples why we call them relations. And then in this factorization over the factor base, you will get a bunch of exponents in the factorization. This is also a type of logarithm method if you want. And then you can do some linear algebra on these exponents to solve the original problem. Okay, so let's do maybe the examples. It will be a bit more concrete. Okay, so first consider the factorization problem. So we have our integer n that we would like to factor. I'm writing little n as the number of bits. Doesn't matter too much for now. And this factorization method relies on the following reformulation. We will try to find a and b such that a squared is congruent to b squared mod n, but a is not plus or minus b. Of course, that wouldn't be very interesting. And in this case, well, you can rewrite this as a plus b times a minus b equals 0 modulo n. So it's divisible by, this product is divisible by n, and in particular, the GCDs of this with n and that with n will hopefully be non-trivial. If a and b are sufficiently random, satisfying this relation, you'll get some non-trivial GCD here that will give you a non-trivial factor of n. So the whole problem is to find a relation of this type. So this is the kind of multiplicative relation that I was mentioning at the start. Okay? So how do we do this? We choose a factor base, b, and that's going to be the set of primes up to a bound y, and we will see how we select y in a bit. So that's a finite number of primes. And we'll repeat the following. We generate a random element modulo n, and we square it. And this is going to represent some part of one side of this equality, and we will try to complete the other side with a square. So you have this element c squared modulo n, and then you lift it in z, like you think you take the representative that is between 0 and minus 1. Okay? And this integer, you try to factor it over the factor base. So sometimes it's going to factor, sometimes not. When it factors, so when c prime is smooth, you record the following relation. You've got c squared equals a product of the primes of your factor base modulo n. Okay? And now, what you would like to do is take a certain product of these c's on the left, such that on the right, all the exponents that you get are even, because that will mean exactly that you have found a square. Okay? And so this is only a problem about the exponents. In fact, just about the exponents modulo 2. You want to find a linear combination of these vectors of exponents that is 0 mod 2. So it's exactly computing a kernel mod 2. So you do this kernel computation, it's linear algebra, and it gives you a combination of these relations that is a square. From that you can compute a and b, so a will be the product of the c's, and b will be the product of the pi's with the exponents divided by 2. And hopefully this will give you a non-trivial factorization. I mean, if you do it randomly, it will usually give you a non-trivial factorization. So let's see how you should choose the parameters for this to actually be efficient, I mean somewhat efficient. So we are constructing essentially random elements modulo n So it's not true that they are really random because they are squares, so they're not completely random. And we are hoping that they are Y-smooth. So the analysis that I will do here is not like a proved analysis. It's more of a heuristic to give you an idea of the running time. You have to be more careful to make it an actual rigorous analysis. But so you have the following theorem, which is if you take random integers between 0 and x, then they are Y-smooth with probability essentially u to the minus u, where u is log x divided by log y. So this is an actual theorem, but we will apply it to elements that are not actually random. So we just use this as a heuristic. We will pretend that our elements actually behave exactly like this. And so we make the following choice. We take y, which is exponential of square root of n. So n is the number of bits of big N. So it's log of big N, if you want. And so that what is u? Well, log x is log x is constant times little n. Log of y is actually square root n. So u is a constant times square root n. Okay? And therefore, the probability of finding something smooth is u to the minus u. So the number of times we have to try to find a smooth element is u to the u, which is therefore, well, exponential of that times log of that. Okay? So essentially, exponential of square root of n trials. And of course, just finding one is not enough because we are constructing a matrix and we want it to have enough columns to have a non-trivial kernel because that's what we want at the end. So we want to repeat that as many times as the number of rows of the matrix. And what is the number of rows? It's the number of primes in the factor base. So that's at most y. Okay, so also this number. So you repeat this number of times this, which is also exponential subtotal of square root n. So that's the time it takes. And then you do linear algebra of that size. So it's polynomial in terms of that size. So it's again the same complexity here. And so if you add this up, you get this sub-exponential running time. So that's not so that's sub-exponential, but not polynomial. We don't know how to do this. And if you remember from the last lecture, I had told you that you could put an exponent 1/3 here, which is better. And I'm not going to tell you how to do this, but I mean, it's a refinement of these kind of ideas where you do some extra work to have integers that are more likely to be smooth. This is how it works. Okay, so that's the factorization example. Let me give you another example. So the discrete logs example. So recall the problem. The problem is that you're given a generator of fp star. I'm going to do it just over fp, not other finite fields. And you are given an element that is, well, a power of g. And we want to find the exponent. That's the discrete log of h. So we're going to use again a factor base algorithm. Consider the set of primes up to y. Again, we'll have to adjust the value of y. And you repeat the following. You generate a random exponent z and let r, which is g to the z mod p. And again, you think of this as an integer between 0 and p minus 1, and you try to factor it over the factor base. And if it is, you write a relation like this. You have an element here of which by construction you know the discrete log equals some product of these primes. And what you want to do is to collect enough relations like this to be able to invert the whole system and deduce the discrete log of all the PIs. Okay? You're given the discrete logs of various combinations of the PIs. If you have enough of that, you can deduce the discrete logs of the PIs. So that's linear algebra modulo p minus 1. And if you collect enough relations, you can do this. And then finally, if you want the discrete log of h, which was given, I mean, this is a pre-computation, really. You can draw random z's until g to the minus z times h, again, mod p seen as an element between 0 and p minus 1 is smooth, factors over the factor base. And if it's smooth, well, you write it like this, and you know the discrete logs of the pi's, and this, obviously, you know the discrete log, so this gives you the discrete log of h. Okay. So I'm not going to do the complexity analysis. It's similar to the one we did before. You have to take y, which is large enough, etc. Okay, third example of this type of algorithms, computing S-unit groups and at the same time, well, class groups and unit groups. So we have a number field and we want to find the S-unit group. In fact, we're going to take S large enough so that it generates the class group. And so it will work like this. So our factor base, so I mean, you can call it B for the factor base, but that's also the S that we think of when we think in terms of S units. It's going to be a set of primes of the number field, all the prime ideals of norm up to a bound y, again, that you have to choose appropriately. And you repeat the following operation. You generate random elements in the ring of integers by taking, well, linear combinations of small elements. And you look at the ideal generated by U, and if it's smooth, which is the same as saying that U is an S unit, then you obtain a relation. So it's a relation in the sense that it gives you a relation between the prime ideals P1 to Pk in the class group. This is trivial in the class group. This gives you a relation between the classes of the Pi's. Okay, and so you collect S units like this. And if you remember last lecture, if you have a generating set for the S units, you can recover the class group and the unit group as respectively the co-kernel and the kernel of the valuation map. And the valuation map is just this set of exponents. And so if you have enough relations to get the full S unit group, then this gives you the class group and the unit group. Now, the only problem is how do you know when to stop, when you have collected enough relations? So this actually uses an extra termination criterion, which is the analytic class number formula. So under GRH, you can compute an approximation of the class number times the regulator of your number field. And it gives you a condition that you can test on this set of relations to be sure that you have finished, that you have the full set of relations. Okay, so this was my last application of linear algebra. And, oh no, sorry, I had another, this was the last index calculus application. Let me give you an application of a completely different type. You are given an integer, a sequence of numbers in some, ring that you're interested in, and you want to guess some recurrence on this sequence with, linear recurrence with polynomial coefficients. Or I guess you could put other types. And here's the method. You choose a bound on the degree of the polynomials and a bound on the order of the recurrence, like the number of terms here. And you simply look for linear combinations of all of these terms that is actually satisfied for many values of n. You're given sufficiently many values of n, and you want to make this an over-determined system, otherwise it's completely useless. And that gives you a guess for a relation of this type. And then depending on the context, you can prove it or do something else with it. So there are various variants of that. You can guess, you can consider the generating series of your sequence, and then having a recurrence relation like this is essentially the same as having a differential equation with polynomial coefficients on the series. You can also look for an algebraic relation for the series, etc. You can do a lot of variants. You can solve the differential equation symbolically to get formulas, etc. I mean, you can do things around this. Okay, so now I want to go to my second part of this lecture, which is about lattices. So it's also some kind of linear algebra, but with an extra, slightly different flavor. So what are lattices? So we start with a finite dimensional vector space over R. And so a subgroup L inside of V is called the lattice. If the following condition holds, you can say either that L is generated as a group by an R basis of V, or that L is discrete and the quotient V modulo L is compact. That is the same. And when I will talk about morphisms between lattices, I mean maps that are linear from one lattice to the other and that preserve the Euclidean norm, okay, that preserve these distances between the elements. Another way to see lattices, instead of seeing them as being contained in a vector space, it's essentially equivalent to think of just z to the n, but equip that with the Euclidean norm. Okay, and because you can always find an orthonormal basis for a vector space with a Euclidean norm, these two points of view are equivalent. So what are we going to do with lattices? Well, here are the problems, some problems that you may want to solve for lattices. So the first one, so you're given a basis of a lattice as input. First problem is the shortest vector problem, meaning you want to compute a shortest non-zero vector of L. Okay? So imagine, maybe I will draw some pictures. Yes. So you are given a basis of your lattice, usually not a very nice one like this, and here, and so the lattice is the set of linear combinations of those. So like, I guess it will look something a bit like this. And here, for instance, you have a shortest vector that is, I guess, this one. Whoops. So this is what you're given as input. It's a basis, and you want to find a shortest vector like that. Okay, so that's the shortest vector problem, abbreviated SVP. You have the closest vector problem. Sorry, this should be a CVP, and that's a typo. So you're given an element of the vector space. I have another color. So maybe like here. And you want to find the point in the lattice that is closest to it. So for instance, here it would be, I guess, that one. Okay? Then another type of problem that you may want to solve is to compute automorphisms of a lattice. So automorphisms in the sense of morphisms, as I told you. So linear maps that preserve the lattice and the metric, the Euclidean norm. So that's going to be a finite group. And closely related, the isomorphism problem, you're given another lattice and you want to know if it's isomorphic to L. You also have variants of these problems. So what you will call gamma approximate versions for a certain gamma means, for instance, you don't want to, you're not asking to compute just only necessarily a shortest vector, but something that's at most gamma times the length of a shortest vector. Same for CVP. And you also have variants not using the L2 norm, but using the LP norm that are also interesting. Okay, maybe this is a good time to take a break. Yeah, so let's describe algorithms for solving some of these lattice problems. So probably the most important algorithm for lattices is the Lll algorithm due to Lenstra and Lovács. And it solves, well, not quite the shortest vector problem, but the relaxed version where the relaxing parameter is exponential in the dimension, c to the n. And it is a polynomial time algorithm, so you can use it for reasonably large inputs. And in practice, I mean, it's quite good because the C that you see in practice, it's better than the one you can prove, and it's approximately 1.02. So C to the n, of course, it's exponential in the dimension, but with small c, for dimensions up to 100, like it's not so large. And it produces a short and almost orthogonal basis, not just a single vector satisfying that it's a solution of 2 gamma SVP. The whole basis is actually a nice basis. So we call this a reduced basis of the lattice. So that's one first step. So it's reasonably fast, polynomial time, and gives an exponential approximation. But now, what if we want to solve actual exact shortest vector problem? We also have algorithms for that, but much slower. So there's 2 families of algorithms for that. There is the enumeration algorithm family, which work like this. You compute a reduced basis of L by LLL, and maybe, well, sometimes you make it even slightly better. And then you enumerate a set of linear combinations of the elements of the basis that is guaranteed to contain a shortest vector. So it's possible to give bounds on the coefficients that guarantee you that among the whole set that you enumerate, there has to be the shortest one. And this takes, well, more than exponential time. So it falls a little bit outside of my complexity classes from earlier. Takes only polynomial space. This is actually nice because memory can be expensive. But so this is practical in moderately big dimensions. And there's a second class of algorithms called Sieve Algorithms, which people used to believe not to be practical, but nowadays these are the ones that break the records. So you first compute a reduced basis of L, and then you compute many vectors in L by taking random linear combinations of your basis, but here you don't take all the possible combinations, just a random set. And then you try to find differences between pairs of the vectors that you enumerated that give something shorter. And you keep repeating until you can't anymore. And so for this to work, you need to have enough vectors here to have actual pairs that are shorter. If you compute too few vectors here, they will be far apart. You'll never have pairs that are whose difference is shorter. So this is where the complexity comes from, essentially the number of vectors that you need to be able to do this. And so it is better than this one, but still exponential time. Okay. One problem with this is that it's also takes also exponential space because you have to store all of these vectors that you want to compare essentially pairwise. But still, you can make it work nonetheless. And it also works for LP norms, not just the Euclidean norm. And just to give you an idea, currently, using these methods, the record is in dimension 180 for these. Okay, so this solves exact SVP, but now we have these two extremes. We can solve reasonably fast gamma SVP with gamma that is exponential in the dimension and exponentially slow, we can solve exact SVP. But actually, by mixing these two, you can produce a continuum of algorithms that give approximation factors between constant and exponential, and that appropriately take more or less time. And this is the point of the BKZ algorithm, Block-Korking-Zolotareff. So this algorithm has an extra parameter called block size, usually denoted beta, between 2 and n. So 2 would be essentially the same as LLL, and beta equals n would be just using an exact SVP algorithm. And you have the whole set of choices in between. And it's going to make a polynomial number of calls to an exact SVP solver in dimension beta. So it's going to take a set of beta vectors and project them to a quotient space to produce a lattice in dimension beta, solve the shortest vector problem there, and from these short vectors, lift them back to the original lattice and use that to improve the basis over and over and over. Okay? And so it's going to make a polynomial number of calls to this solver in dimension beta, which by the previous algorithms, we can solve in time exponential in beta. So the time it takes is something polynomial times 2 to the O of beta. And what is the quality that you get for that? Well, it solves gamma SVP with gamma, which is C to the n over beta. Okay, so for instance, if you want something medium, you could take beta that is square root n, and you would get exponential in square root n in time exponential in square root n as well. So just to give you an idea, in practice, you get this C to the 1 over beta is approximately 1.01 for block size 30, which is something that you can actually use. And like LLL, it doesn't just give you a solution to gamma SVP, it produces a whole reduced basis, a nice basis, accordingly nicer compared to LLL, depending on the block size. Okay, so that was for SVP. Now let's look at the closest vector problem as well. So here again, you have approximate algorithms and exact algorithms. So one approximate algorithm is Babai's algorithm, which I will show, I guess, on a picture on the board to explain it. So I hope I have enough of them. And let's say that our target is maybe here. Okay, so first maybe what I should say is one basic idea that you could use is you take this vector and you express it as real combinations of the basis, and then you round the coordinate to the nearest integer. That will give you an approximation of the closest vector problem, but the type of shape that it will give for where the points can land when you reduce them is going to be this kind of shape. And it's not so good like near the ends here. This is quite far from there. So Babai is an improvement on that, where instead of doing this, you're first going to look for an approximation in one direction. Okay, am I going to be able to draw that like this? So, well, here again, it's just rounding the coordinate. But then in the second coordinate, instead of just using the coordinate on the vector here, you first project orthogonally to the first one. And so you will get something more like this. Okay. It will produce things that are a bit more rectangle-like, something like this. And okay, you can reduce your point to here. Well, okay, I didn't really use that point. And so this gives a better approximation than the basic take the coefficients and round them algorithm. So this is just polynomial time, and the quality of approximation that it gives depends on the quality of the basis, so I'm not going to give the actual estimate here. When you want to solve exact closest vector problem, one technique that is useful is what is called Canon's embedding, which uses an extra dimension to solve your problem. So, okay, maybe I will draw another picture for this. So suppose that you're trying to solve your SVP problem in this space where this is 0, you have maybe a basis here, and your target that is there. And the way you're going to do it, you're going to add one extra orthogonal dimension here, and you will lift this target point to a vector here. By picking a certain height here that you want to add. This is a parameter. You can choose it whichever way you want, and you will try to find a short vector, so solve SVP in the resulting lattice that has one more dimension. And the reason why this actually works is if you look at what is the norm of a vector from this lattice, it's just this, which is the distance between an element of the original lattice minus possibly a multiple of the target that we had, plus this extra factor. But what you really want is lambda to be 1. So you use this alpha as some kind of penalty for short vectors so that it forces lambda to be small. And so if you manage to get lambda equals 1, and this is small, then this is really a closed vector. Okay? So using these kind of techniques, you can show that you can solve exact CVP in time exponential in n. And variance of that also works for LP norms, not just for the Euclidean norm. Okay, now I want to mention automorphisms and isomorphism algorithms. So there's mainly two algorithms. There's one by Plesken and Souvignier, which uses the following idea. You take a short basis of your lattice, and you look at all the possible images of the short basis, because the isomorphisms have to preserve the distances. You know from the length of the domain vectors have to be the same as their images, and so you have a finite number of possibilities, and you can enumerate them all. And then there's many ways to make this actually faster. You can exploit some group theory because the automorphism group is a finite group, so there are group theory tricks and other kinds of tricks to make this faster. It's also possible in this algorithm to include extra conditions. If your lattice is not just a lattice but has extra structure, you must preserve some extra bilinear form, whatever, commutes with some action of other endomorphisms, you can incorporate that. And the complexity is something quadratically exponential, so you can apply this only in quite small dimensions, maybe, I don't know, 10 to 12, maybe something like this. This was a bit outside of my classification, so I didn't really know what to call it. So this is one algorithm, but that is actually used in practice. But there's another one which is theoretically faster, but completely unusable, really. And it uses the dual lattice in a certain way. It searches for a special vector in there. And the complexity is just above exponential. Okay, but this is unusable in actual examples. Okay, one quick mention about another kind of lattices. You can also do lattices over function fields. So in this case, you will replace your real vector space by a vector space over the field of rational fractions over a field, well, let's say a finite field. And your L is going to be the set of linear combinations of a basis with coefficients that are polynomials. So you replace integer by polynomials and reals by fractions. And you have a notion of size instead of Euclidean norm, which is just going to be the maximum degree of the coefficients, where the degree of a rational fraction is just degree of numerator minus degree denominator. Okay? And the great thing in this setting is that you have a polynomial time algorithm that actually solves SVP. So you can do everything in polynomial time. Okay, I'm not going to say more about the uses of this, but it can be good to keep in mind. And to finish, I want to present a few applications of lattice algorithms. So first, let me give you a bit of a rule of thumb to identify what can be a lattice problem. So there's mainly two uses that you can make. Either you have some object, and you can do linear transformations of it, and you're trying to make it smaller. Maybe just because you want it to be like smaller in memory, or because making it smaller will make other operations faster, or something like this. And typically here, you don't have a precise constraint on how much smaller you want it, you just want it reasonably small. And another type of problems is if you have a problem that is typically something that you would identify as linear algebra, like in the first part, but you have size constraints. Some sizes are imposed. So let's see some examples. So one example of the first one would be the following. You're in a number field and you've computed, say, a basis of the ring of integers. But there are many different bases and they are not all as good as each other. And so you want a small basis because it's going to make, for instance, all your arithmetic operations faster. And you can simply use, LLL or better reduction on the ring of integers with the following norm that takes into account all the complex embeddings of your field. So taking this norm on the ring of integers will give you a positive definite quadratic form, so you really get a lattice, and you can compute reduced basis with respect to that. And doing that, that reduces the cost of arithmetic operations. But you don't really need a precise guarantee on the output for that. Okay, an example of the second type is the knapsack problem. So it's the following problem. You are given a bunch of integers, x1 to xn, and a target sum s, and you want to find a subset of x1, xn whose sum is exactly s. So to make it an actual lattice problem, you have to first, reformulate it as a linear problem, and you will simply write it like this: sum of some coefficients times xi equals s. That's the linear part. But since you wanted just a subset, you have this size constraint, which is that the coefficients have to be 0 or 1. So that's where the size constraint is. And once you see it like this, you can reformulate it as a lattice problem by writing down a lattice like this. Did I take the transpose of what I wanted? I think I wanted the transpose of that. Okay, it's, I'm giving the lattice in rows instead of columns. Okay. And so if you look at linear combinations of the columns here, you will get something small as long as the sum here is small. That is, if the sum of the xi's is close to s, and ideally you want it to be equal to zero, I mean the sum to be equal to s. And the fact that you have ones here will impose the coefficients to be small. Okay, so depending on the size of the xi's, solving a short vector problem on this lattice will actually give you a solution of the original problem. Okay, a few more applications. Maybe I will skip some. So one nice application is to guess an integer linear combination of some real numbers that you only know approximately that could be approximately 0. So you're given a bunch of real numbers. You want to know if you have an integer linear combination with small coefficients that is approximately 0. And so you can write a lattice, well, quite similar, in fact, to the knapsack that we just saw, for which a short vector will give you a linear combination that satisfies something like this. So just to give you an example, 2 weeks ago, I had a colleague who had a new algorithm to compute a certain quantity, let's call it R, and he didn't have any, I mean, it's a hard quantity to compute, so he didn't have any examples to see if his program was valid. So he was looking for a way to validate his results, and for that we found a formula that was proved in some paper that was about this R, so a certain expression like this, so L, omega, D, doesn't matter what they actually are some quantities that you can compute, and the claim was that this was supposed to be a rational number. So this is something you can test if you can compute it to finite precision using continued fractions. I mean, you can check that it looks like a rational number. And unfortunately, when looking at these values, it didn't look at all like they were rational numbers. So what did we do? We thought, well, maybe there's a typo in the formula. And since we didn't know how to prove the formula, instead of looking at the proof, we tried to do the following, to look for an integer linear combination of the logs of the things that appear here. And I did approximately 0. So we took like log R, log L, log pi, log omega, log square root D, and log of some small integers, so small primes. And the algorithm gave us this relation. So it looks like there was a small typo that this square root D should have been a D instead. And we tried it on a few other examples, and it also looks like it's like this. So we haven't yet asked the authors of the paper if it's actually a typo, so we'll double check first. But this is a way of checking maybe mistakes in this kind of formulas. Okay, a variant of that is looking for algebraic relations satisfied by a single complex or real number given by approximations. You just use the same thing as before, but with powers of alpha. Okay, I'm not going to give more details about this. Another useful application is one that I mentioned in the algebraic number theory lecture. Namely, you have a number field with a certain defining polynomial, and you want to replace it by a smaller defining polynomial. And so a way to do this is to compute the ring of integers. Again, compute a reduced basis of the ring of integers, as I mentioned earlier, and find among the basis vectors of a ring of integers or some combinations an element that actually generates the field. And then you output the minimal polynomial of this element beta. And because it was small with respect to T2, the coefficients of Q are going to be relatively small. Okay, some other application, again in algebraic number theory. So recall that we talked about reconstruction of various type of numbers, integers, rationals, polynomials, rational fractions. You can also use lattice algorithms to do it in number fields. So if you're given an element modulo an ideal, let's say that it's in the ring of integers, and you know that it's something about its size, that it's reasonably small, and you want to reconstruct the actual V. So if the ideal is just the set of multiples of an integer, then you can simply reconstruct all the coefficients independently. You know the coefficients modulo A, and you can reconstruct them as integers. But if your ideal is not of this type, then this doesn't work. And in this case, you can reformulate it as a closed vector problem, because the problem is simply you're given V prime in ZF, and you want to find something that is congruent to its modulo A and that is small. So that's the same as saying that you want to translate it by an element of the lattice A to obtain something small. That's exactly the closest vector problem. And well, okay, so if you analyze precisely the bounds, etc., you can give bounds on the element and, depending on the ideal, to be able to reconstruct. Now, let me give you the actual historical example that sort of started, actually, the paper in which the Lll algorithm was described for the first time. And the problem was to find, to factor polynomials over Z or Q. So this is something I told you that you can do it in polynomial time, but we didn't talk about how to do it. And it actually uses LLL, the Lll algorithm for lattices. And it works like this. So you take a prime number, and you make sure that your polynomial is square-free mod P. And you factor it over Fp, so this we know that we can do efficiently. And we consider one of the non-trivial, okay, I said non-trivial factor, but here I really mean irreducible factor. Okay, take Q an irreducible factor mod P, and you lift this factor of P modulo some higher power of K. You can do that with the Hensel type of lifting. And because you chose P in a way that your polynomial is square-free mod P, there's a unique factor of P in Z that satisfies the property that it's divisible by Q mod P. There can only be one because of this square-free property. And you're going to try to find this R. So this R, it's a single polynomial, it's fixed, but you can increase the power of P as much as you want. And because of this, the following happens. So R is going to be a short vector in the following lattice. You take the set of polynomials of bounded degree such that the polynomial mod P to the K is a multiple of Q. So this really, you can convince yourself that this is a lattice. This is just a linear condition here, being a multiple of a given polynomial. And so if you take K large enough, you can show that the LLL approximation of the shortest vector problem is sufficient to actually find R in this lattice. Okay, and so that's how you actually find this non-trivial factor R. You can divide by that and then continue. Okay, and I will finish with a sketch of an application of isomorphism testing of lattices. So I won't give the details because it's a complicated thing, but I want just to mention it because it's interesting. So the problem is you're given a number field and you want to compute a set of generators and usually some other kind of information that I'm not going to tell you about in details for the group GLN of Z. N by N matrices of ZF, of the ring of integers. And there's an algorithm due to Voronoi, which follows roughly the following sketch. It uses a special kind of lattices, which are called perfect. And it goes as like this. You start with the first perfect lattice, and you repeat the following. For each perfect lattice, you have a notion of its neighbors, which are other perfect lattices that you can find by some geometric means. And then when you have these neighbors, you can test if they are to some of the previous perfect lattices that you had. And then you keep going, you compute neighbors, and you test if they're isomorphic to the previous ones, etc. And, well, Voronoj's theorem is that there's only finitely many perfect lattices. So this will eventually stop. And once you have the whole set of perfect lattices, you can exploit their geometry to deduce information about this group GLNZ, so generators and other kinds of interesting information. Okay, so that's all I'm going to say about this, and thank you for your attention, and you can ask questions.